Welcome to our Solutions for NanoAnalysis podcast, brought to you by Bruker NanoAnalytics. We look forward to bringing you a new podcast regularly. My name is Cody Morton. I'm a marketing communications specialist at Bruker NanoAnalytics and an information enthusiast. If you like to learn from specialists in their field and hear what technologies are solving their problems, you will enjoy this podcast. Every session, we will focus on a different problem that our colleagues face in the lab and in the field. Some of the solutions will be a variation of ideas you may have heard before or even worked with. We will bring you these topics in a new and interesting way and introduce you to updated and thought-provoking results. We will talk about how the problem was dealt with in the past and what we're doing to solve the problem now and perhaps even envision future solutions. Join us as we talk solutions with a variety of scientists and technicians in many different industries in the Solutions for NanoAnalysis podcast. So thank you for joining us, Dr. Meiken Falke. Who are you in the world of Bruker?
Yeah, hello. Thank you for this interesting opportunity. I am called Global Product Manager TEM EDS, and that means I'm responsible for energy dispersive X-ray analysis on electron transparent samples or specimens with really small structures, nanostructures. And the responsibility within Bruker includes everything connected to product management. So application, R&D, hardware, software development, bringing the developments to market and make sure that we stay on track with what we do next.
Excellent. And how long have you been with Bruker?
Yeah, I joined in 2008, so it's quite a few years now. And it was always sort of on the same topic. Starting as an application scientist, but very quickly I moved to product manager.
Excellent. And joining us also is Hosanna. Hosanna, introduce yourself, please.
Hey, I'm Hosanna Lillydahl-Schroeder. Try saying that 10 times fast. I am a senior application scientist for the Americas at Bruker, and I cover EDS for TEM and SEM, WDS, micro XRF on-SEM, as well as EBSD and TKD.
Very good. And Hosanna, you're going to be talking to Meiken today about elemental analysis of semiconductors. I'm going to go ahead and jump out of the way so that you guys can start the conversation.
All right. Thank you, Cody. So Meiken, what brought you to where you are today with science and being an EDS product manager at Bruker?
Well, I was always interested in science. So since I can remember, I wanted to understand what everything consists of, how things work, how life works. So I guess I always had a bit of an analytical mind. And probably as many also, as a young girl interested in space research and always interested in nature. And I'm also interested in art, which is an interesting aspect here. So on my way, I tried different topics of physics. So I studied physics because I was thinking at the time with physics, you can explain everything. So that's why I studied physics. And I tried several topics in physics and more or less by accident ended up in microscopy, where I stayed because I was really happiest in microscopy. And it also combines analysis and art in a way. So for instance, if you want to usefully show what you've done in microscopy or in diffraction or in spectroscopy, it's good to have a bit of an understanding of several dimensions and colors and how they mix and how grayscales works and false colors or pseudo colors and so on. But that's the general interest. So the EDS part is a bit of a funny story. I was lucky to be one of the first setting up user facilities for aberration-corrected microscopy. And there we had really high-end aberration-corrected microscopes. That was at the SuperStem laboratory in the UK. And as a spectroscopy technique there, we used EELs. Now, EELS is a really powerful technique, and it comes with really high energy resolution now, reaching infrared spectroscopy level. And at some point, somebody came to SuperSTEM and said, shouldn't we add EDX to our TEM? And we all said, no. We do everything with EELS. We don't need EDX at all. And then one day I was tasked to analyze a specimen, which was tissue from the lung of a patient who lived very close to a road with very heavy traffic. And I was asked, couldn't you identify all the nanoparticles in the lung of this patient? And I tried hard, and I'm pretty sure I didn't find all the elements which were there. EELS is very uncomfortable to use when you want to have an overview of all the elements present in a sample. And that's where I realized we can't do everything with EELS. And then still, I never imagined that I would be working for a company producing EDS systems and EDS tools. But now, since I joined, since 2008, I realize how powerful EDS can be, particularly when analyzing a mix of all sorts of unknown elements.
So could you give us some additional examples on where and how EDS has some clear advantages versus EELS or other analytical techniques for TEM?
Well, to broaden the first example with the lung tissue a bit, of course, in biological specimens, life science as a whole, where we always have a mixture of all sorts of elements, light elements, heavy elements, unknown combinations of elements. So EDS is really powerful there. And it has been shown also to be working in cryo samples, frozen in vitreous ice, for instance. Also forensics comes to mind, art and conservation, old stuff, what does it contain? So anywhere where many elements need to be identified, and all these topics might be used for next podcasts maybe. And thinking of life science, life on Earth, there's this little remark on space. There I was also lucky once I was part of an experiment together with Rhonda Stroud of the Naval Research Lab. And she looks at the combination or element combination of stardust. And this is, well, another thing where you don't know what you will get. And EDS was really powerful, identifying the combination of elements in the stardust. And thinking about space leads back to minerals on Earth. I believe they also come in all shades and combinations. But I guess this is where you are more knowledgeable than I am.
Yeah, I have 2 degrees in geology, as far as that goes. So guilty as charged. But yeah, it's quite an interesting problem, both looking at space dust, that sort of thing, the real sort of building blocks of life, and also where all the raw materials come from that make semiconductors, basically as minerals, as far as extracting those, refining them, and then, turning them into computer chips and other pieces of high technology. So that provides a nice segue into semiconductors.
Yeah, you are right. We are supposed to talk about semiconductors. And that was also, the next group of materials I wanted to mention. And that is what doesn't come to mind immediately. Actually, one aspect is that in modern semiconducting devices, there is a surprising amount of different elements mixed together. And EDS is again useful to get an overview of all the whereabouts of these elements. And the reason is that now, and also a few 10 years ago it started, but now it's even more visible, that completely new approaches in the design of materials for semiconductor industry are needed to produce smaller and smaller stable structures. This is because just geometric scaling of the devices doesn't work anymore for future miniaturization. Now elements and element combinations are needed for which the properties of interest, such as conductivity, resistance and the performance they have during making them into really thin, fine structures are suitable at very small dimensions, which may be totally different for these materials compared to the situation at larger structure sizes. So for instance, using cobalt instead of tungsten and copper as a thin interconnect material falls into that category. And there are many more changes of materials, basic materials, material combinations in semiconductor industry to be expected, so that the further miniaturization can go on. And then you have all these strange materials mixed and deposited or somehow manufactured into very thin functional layers. And then these thin layers, they sit on top of each other to build, for instance, thin resistors or diffusion barriers or interconnects. And then it's important to see, are they where they are supposed to be? What happens at the interface of these structures? Are there any failures? And that is where EDS is a really powerful tool. And then there is more to semiconductor industry. It's not just the functional materials which are of interest, but also other things which might cause device failure and need monitoring and investigating. For instance, remains of the etching process, like fluorine from fluoridic acid or chlorine. And it's important to see where they are and if they have any effect or any unwanted effects. So this results in a mixture of light and heavy and medium-sized elements. And as I said, EDS is really good at tackling those. And it is particularly good for TEM because of the low background. So EDS is absolutely ideal because of a high peak-to-background ratio for electron transparent samples. And TEM is needed for high spatial resolution. And therefore, EDS in TEM is the ideal tool and used a lot in semiconductor industry.
So since we're talking about different length scales, basically, and further miniaturization of various chips and semiconductors, other materials in that particular industry, what type of length scales would be seeing use for in these studies as far as application for TEM versus SEM? What would be some good or relevant examples where each technique would or type of microscope would be appropriate?
Oh, that's quite a broad question. So I started out with TEM. So the length scales there, we are now at, I don't know which node, but it's always, we are talking about a few nanometers. So if we want to judge the functionality of the devices on the nanometer scale, we need to analyze at least one order of magnitude better. So we need to be on the atomic scale that is done in TEM. But of course, on the nanometer scale or atomic scale, we only see a very small piece of our specimen, and therefore SEM or larger scale investigation is also very important. And I know that SEM and used a lot, specific SEMs or specifically designed SEMs with specific additions of analysis are used also to evaluate whole wafers or wafer surfaces for contamination or functionality. Also, whole chips are getting delayered, and one looks at different levels, I guess more on the length scales of several tens or 100 nanometers and micrometers. And if we are talking whole wafers, then this is then already centimeters. The scale so goes from really large to very small, and from I think before there sits micro XRF and then SEM and then TEM. So all of these microscopes have advantages, but let's stick with the TEM first. And when we talk about TEM, we need to relate EDS to EELS. That is important. So EDS is energy dispersive X-ray spectroscopy. EDS, or some people like to call it EDXS because it has 4 letters like EELS. And it uses the characteristic X-rays emitted from an ionized atom when the empty energy levels are filled again. And with that, very distinct sharp element lines are formed. These are the characteristic X-ray lines, and they sit on a very thin or low or small Bremsstrahlung background. In EELS, however, the complete energy loss of the electron is analyzed. So that means the electron loses energy for many different processes, and only one of these processes is the emission of characteristic X-rays, which EDS looks at. EELS has hidden within itself a much more complicated collection of effects, which we can see in the EELS background. So the background at a particular energy represents the overlap of all energy losses below this energy edge. And it's very complicated. And then sitting on top of this complex background is the EELS edge. And then there are particular elements which overlap or have so-called delayed edges, long range, broad edges, and like 3-5 semiconductors, the heavier elements used in 3-5 semiconductors. And this is quite uncomfortable to use for element ID and quantification. Then there are people, they say, oh, we use just imaging. The dark field contrast tells us where something heavy and where something lighter. But this also fails for 3-5 semiconductors and also for the mixture of elements, which I mentioned before. Because as soon as you have more than one heavy and more than one light element mixed, it's difficult to judge just from the image where is what and where is which element. So for this, EDS is really ideal. It can use energy ranges of up to 80 keV, which is really difficult to do easily and quickly for EELS.
Yeah, and as an aside with EELS, don't you also have issues with deconvolution with that technique as well?
Yeah, this deconvolution is maybe not as straightforward as with EDS, since, as I mentioned, the background is so complicated, and all processes which have happened at energies below the energy I'm looking at are convoluted with each other and need to be tackled when I want to subtract the real background. But maybe there's also another issue. So EDS has been used, as far as I believe, by many more people and in more industries, and it's broader spread, and there has been more effort put into a quick and simple EDS analysis. And maybe if there would have been so much power and so many companies dealing with EELS, some of the processes would be also at least appearing more simple, like a push button technique as in EDS.
Yeah, that probably explains a couple papers that I discussed with battery research or customer doing battery research some time ago, saying they'd seen some very, let's call them creative diagrams showing, excessive amounts of elements being deconvolved from an EELS spectrum. So that's a problem in any technique, I think.
The EELS, the complex EELS edge tells us more about the bonding and how a material is bonded and with which other element it's bonded at which distance, and this causes ripples on the background, which need to be interpreted in the correct way and not just like each bump must be an element. That's not true for EELS.
Fair enough. So going back to your discussing that, trying to use dark field contrast images to, determine differences between elements, basically use those instead of, say, EDS or EELS or some other elemental analytical technique. Arthur, on that note, if you're dealing with, say, multiple heavy or multiple light elements, moving towards the light elements, like, say, nitrides used in semiconductors, also carbon, boron doping. And then obviously in terms of life science topics, you're dealing with typically lighter elements rather than heavier elements that we would be using for semiconductor applications as well. So, based on all that, what are your thoughts on analyzing light elements by EDS? Because we can also obviously get into some deconvolution problems in the low energy side, where you have, many lines, say L, M, N lines for heavier elements overlapping with K lines from our lighter elements in those areas.
Yeah, true. There are quite a few overlaps, but that's maybe one step ahead. I guess where the question also comes from is, formerly EDS, to use EDS for light elements was an absolute no-go. So that's why it's not widely spread yet in life science, because formerly when we were still in the lithium drifted liquid nitrogen cooled EDS era with beryllium windows, the detectors were not so efficient for the light elements, but they have become so good now. We can use light elements of different thicknesses. The net on which the light element sits, so the grid on which the light element is sitting, the silicon grid, gets thinner or is replaced by something else. We get carbon-based windows, or one can use windowless detectors. The efficiency for light elements is so high and also good for deconvolving light elements and overlapping M and L lines, that now the investigation of even boron doping and also nitrides in the semiconductor industry became actually routine. For some element, it's, as far as I see from my own experience, it gets really simple, quite unequivocal. For instance, nitrogen has one line and titanium is overlapping at the same place, but it has a second line toward a higher energy. So these two can be nicely deconvoluted. And we have examples where it's clearly shown that the nitrogen and titanium and silicon whereabouts can be nicely separated from each other. And so titanium nitride and silicon silicon and pure titanium can be identified and also quantified in EDS. Yeah, so that was about nitrogen and related overlaps and so on. And now you also asked about doping of semiconductor materials with elements such as boron or phosphorus, arsenic, and there are more, I think. Well, all of these elements can be identified and quantified by EDS. To which level or minimum mass fraction, to use the right term, that depends on the combination of microscope and EDS technology. The better the microscope, the better the outcome for EDS, and also the better the EDS technology, of course, the better the result will be. And if we have a combination of a high-end microscope with a high-end EDS detector, then that, of course, would yield even better EDS results. Here I would like to mention a paper by Roland Pantel from ST Microelectronics. It was published in Ultramicroscopy, I think even 10 years ago now, and it is describing the analysis of phosphorus and arsenic distribution using EDS, and we are speaking really dopant level distribution. And in that work, one single EDS detector with a light element window was compared to 4 windowless detectors arranged in an annular geometry around the pole piece of one very similar microscope. And they were compared concerning their performance in dopant analysis. I think we need to discuss this high collection angle annular geometry later on during our little podcast. But back to the experiment. So with just the one detector with the light element window, it took about 2 hours to see some phosphorus and arsenic. And that was only possible with heavy pixel binning. And with the newer annular high collection angle arrangement of several windowless detectors, a 200 times increase in X-ray count rate was observed, and it took only minutes to get a much better dopant distribution for arsenic and also the lighter phosphorus. Yeah, and on top of that, the EDS sensitivity allowed even to see the bumps in the EDS background, which is caused by coherent Bremsstrahlung. So this paper is something I do recommend to everyone who is serious about analyzing semiconductor materials.
All right. So from what you're saying, it sounds like EDS is a very, mature technique and well suited for identifying many different elements in the semiconductor industry. Are there any particular examples where EDS has, provided answers to any particularly challenging topics, or do any other, interesting applications stand out to you?
Yeah. So just to repeat, I already mentioned the 3-5 mixtures, which are really difficult for EELs, mix of many elements, finding residuals of manufacturing preparation, also the gallium and platinum from the FIP can be seen in EDS, by the way, but particularly challenging are perceived the overlaps of, for instance, hafnium, tungsten, and silicon, or the overlap of copper and tantalum. But actually, looking at the data, and we have also published quite a few in our webinars, which are sitting on the website, it is well possible to deconvolute hafnium, tungsten, and silicon overlaps and get very clearly the whereabouts of each of these elements. And also copper and tungsten overlaps can be well deconvoluted in EDS. It's not just, they sit on top of each other, you can't do it. No, it's really possible. The one option which we have implemented is what we call the so-called online deconvolution. That is a more simple deconvolution technique doing just several iterations to be fast, and one can check on the fly how the tungsten and silicon and hafnium, for instance, can be separated. And some overlaps need more iterations and need a proper quantification step. But once the quantification procedure is set up, it's just push a button, and then the quantification runs for a minute or a few minutes, and the elements are really well separated. So I've seen that hafnium, tungsten, and silicon, and also tantalum and copper are well deconvoluted already with a few iteration steps, so with the so-called online deconvolution right during the measurement. But silicon and oxygen sometimes need a proper quantification step. Yeah, and as I already mentioned, titanium and nitrogen, yes, they sort of sit on top of each other, but can nicely and easily be deconvoluted or deconvolved.
All right. So you mentioned FIB work in your last discussion here. So speaking of focused ion beam, sort of discuss that with applications to TEM. But earlier I also asked you about SEM and different length scales. So what sort of things can we also do in SEM? Because in some ways, almost with the field emitter technology that's coming out lately, there's almost some blurring of lines there as far as what length scales you can really look at and investigate with EDS in SEM and versus TEM.
Yeah, you are right. So the two techniques are kind of overlapping already. So if we come from TEM, we could first speak about doing TEM in SEM. Of course, one can put a TEM sample into an SEM. It's actually being made in an SEM, so in FIP, right? And it is amazing what is possible in SEM with electron transparent specimens. So there are, depending on the quality of the beam and of the SEM, nanometer scale analysis is possible with a SIN sample, and also TKD, structure orientation analysis, which is important for certain semiconductor parts, can be done also in SEM. It's not as big and not as expensive as a TEM, so it should be used more for evaluating TEM samples. Also, when doing FIP, one can delayer or remove parts of a semiconductor device or structure or wafer, and then look at the different steps or at the different levels which have been set free to check how the element distribution is there. And then we can go bigger. We can also have a bulk specimen in SEM and then look on length scales like several tens or hundreds of nanometer, micrometer. And since I'm coming from TEM, I'm not sure I will be able to cover all, but I know failure analysis of devices, device parts, wafer parts, or full wafers is being done with EDS on SEM. And for that, different detectors are available. Yeah, it depends a little bit. If we, in bulk, the background is higher, but it's also, and one cannot look or check at higher energies. In TEM, we can check up to 80 keV. If you really have a strong overlap at lower energy, we can go up to 80 keV and check which element is really there. In SEM, it's not that simple. And also, if you want to see smaller structures, the acceleration voltage needs to be a little bit lower. But it's amazing what the deconvolution can do, and also how fast one can go if one has the right detector. So there are different detectors available, standard side entry detectors or annular detectors. Yeah, maybe we should talk about that now. What do you think?
Sure. Yeah. So as far as these different sizes and types of detectors, what sort of timescales are we talking about as far as, data acquisition and, time for analysis, that sort of thing?
Yeah, it's maybe, I like to explain things so people can imagine, not just give numbers. Yeah, acquisition times, they reach from hours to seconds. Yeah, that is not very informative. So X-rays are emitted sort of roughly, simply speaking, in a sphere, so around the whole sample. In the bulk situation, it would be sort of the upper sphere above the specimen. And if we have a side entry detector, we cut out only a very small part of that sphere, if you can imagine that. But, or the listener can imagine. But if we had an annular detector right on top of the specimen with a hole in the middle, then we would sort of cover nearly all of that sphere. And that is 100 times more than just cutting out a little piece by a side entry detector. And that's how also these different acquisition timescales are explained. And so if the cutout, the angle under which we look, the collection angle, is a small little piece, we see 100 times less radiation. We can still use it, we can still deconvolute it, but it takes us 100 times longer compared to using an annular detector or several detectors from looking from different sides onto the specimen surface. And that holds for bulk and also for transparent specimens. So there is a side to this which is complex for an EDS manufacturer, but also very interesting. because if we wanted to have many detectors looking at the specimen, it's the easiest to implement them into the microscope. So for the customer, the best solution to be fast is having the detectors integrated in the column, or having the column or the EDS ports being adapted to what EDS needs. And this combination or collaboration between manufacturers of microscopes and manufacturers of EDS is important for the future of the technique, for being able to find elements on the nanometer and atomic scale within seconds and not waiting hours to analyze, for instance, doping levels.
So in addition to reducing time to data by improving solid angle and really integrating that with microscopy vendors, what else do you see as being the future of the EDS technique?
One aspect is the collaboration. I would wish we would have more EDS suitable TEMs and SEMs. I already touched on that a little bit in EELS. There is some acquisition or imaging conditions are good for one thing and others are good for EDS. And manufacturers are already starting to produce microscopes which can be easily tuned between different options and then also be optimized for the EDS option very quickly. We need to be optimized for EDS. We need high collection angles to be fast. One is electron beam damage. So more and more, I also see the requirement from semiconductor manufacturers to avoid beam damage and measure fast. So there we need large detectors. And being fast, having large detectors or large collection angle detectors, this invites for temporal resolution, which means in situ microscopy. So we could check the whereabouts of the elements and what they do and how they behave in changing environment in situ. Look at higher temperatures, for instance, what happens if our devices heat, if the phones become hot on an airplane, what happens and how can we avoid that? How they behave with electrical current, electromigration is a word. So biased specimens in SEM and TEM can be looked at, or what is mechanical load causing. So this is the whole bunch of in situ experiments, which is booming at the moment and of high interest because we now can analyze so fast. Then there is also the 3D acquisition, looking at stuff not just 2D but 3D. We have this projection artifact that we can't really judge in projection what's actually wrong. Like if you get an X-ray from a broken leg, it's better to have a 3D information, like a tomogram. And this is still very complex and done in collaboration between institutes, scientific institutes, and the semiconductor manufacturers. So more simple, more easygoing 3D analysis is also important for the future, and more easy combination of techniques, as I mentioned. Use the good of both sides, EELS and EDS, maybe cathodoluminescence for 3-5 semiconductors, or combine EDS and diffraction techniques, like, for instance, also orientation mapping, EBSD and orientation mapping in transmission, like TKD, which Booker also offers, and look on where grain boundaries are, where the diffusion pathways are in a device. One can see that with TKD. And if the orientation of particular functional layers is the one we want to have, and if there is the right combination of elements in that functional layer, that can be done in combined EDS and, for instance, TKD combined, and that again in SEM. So there are lots of ways for the future.
So where does all of your information and knowledge come from, as far as all you've discussed regarding semiconductors, since you started off looking at lung tissue anyway?
Yeah. Part of it, I'm really grateful to the company I joined 2008. They're dealing with all our different customers. We learn a lot of what needs to be done and what is the interesting way forward. But my dealings with semiconductor industry go far back. So already in my PhD, I was looking at silicides and different silicides and consumption of silicon by silicides for semiconductor industry. And I never lost touch. At the time, that was done in East Germany, close to Dresden, which is these days also sometimes called the Silicon Valley of Saxony, or there is also even a consortium of all sorts of high-tech companies, which is called Silicon Saxony. And we have been always in touch with these people. And then, of course, with Bruker works with all the big names in the industry. Everyone you can think of making semiconductors, phones, and so on is a customer of Bruker. And from these people, we learn, we strive to understand their needs and future needs, and will hopefully be able to adapt our technology and capabilities and analysis speed to what will be needed.
Thank you to our speakers today. If you would like more information about today's topic or to submit a topic idea, please email info.bna@bruker.com. You can also check out more information in today's show notes. Join us next time as we look at a new solution with more scientists and technicians in all sorts of industries.